Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So hi everybody, and hello to all the people who are following online. The topic of the seminar today is Visipedia. It's a project I have been working on with Serge Belongi and our students for the last 3 or 4 years, and I'll focus on some aspects of it. I cannot cover everything. And I hope that people will want to stop me and raise their hands, because there are some philosophical discussions here and there where I always benefit from people's comments and objections, etc. Okay, so some of you have seen this slide, and the question is always, can you name this part of the bird? And this helps me introduce the issue that often we have these visually driven questions, and it's very difficult to answer them given today's technology. And so the knee-jerk reaction is always to go to Wikipedia, at least for me. But if you don't know what to type, it's difficult. So in this case, I typed beak to find out what the thing was. And then I went to pigeon, and then I went back to beak. And after a while, I found in a small print a word that made me think that maybe I had found it, and indeed I had found it. And the name is seer of that structure. Okay, and so it's not only pigeons have it, but also some parrots and some hawks have a seer. This is another instance of the same phenomenon. This is some email, some SMS that my father-in-law sent me, in fact, email from his cell phone. And he wanted to know if I can eat this particular mushroom, because he knows that I pick mushrooms on the Alps. And so by the look of it, I thought he should not even touch it, but I wasn't quite sure. And this was a difficult nut to crack. I went to Wikipedia. I thought roughly I knew what it was, but I wasn't able to make any progress from the entry page, because I thought there would be some field guide that would help me, but no. They tell you, buy yourself a paper field guide if you want to identify the mushroom. And so it turns out that field guides don't work. And in fact, we have experiments that I will not show today that demonstrate that field guides don't work. And if you're interested in why and how do we find out, ask me later. So it's a problem. And we are so used to being able to find all the information we want at our fingertips. In fact, we say it often in our talks, oh, isn't it beautiful? Today we can find anything we want on the fingertips. It's not true. 99% of the material or bits or bytes that are on our hard drives on our internet are images and video. And that's completely dark matter. We cannot access it. And all of us in computer vision know it, and we're working very hard to solve the problem. And so just to go back to the mushroom, the page is there. It's an Amanita pantherina. And so one interesting remark is, if you read it, they tell you that Europeans are convinced that it will send you to the hospital within hours of eating it. And the Chinese have a way of cooking it that makes it very delicious, and you can eat it no problem at all. And so I'm very curious to ask my Chinese friends to teach me how to deal with Amanita pantherina. But I'm not sure I will sample it afterwards. Okay, so so this was the first point, which is not true that the web is fantastic and we find all the information we want at our fingertips. Whenever we have a visual query, we are stuck very often. And unless we can think of words that go with a query, in which case we can make progress. And yet information is there, and so there is a bridge to be built somehow. A second point is that is made by this slide here. And so here, so this little story is, I was at the Gordon conference. I think maybe Rick was not there for once. I usually meet Rick at all of these small, nice meetings. And it was near the park of Yellowstone, and I was walking around Yellowstone, and I found the body of an elk eaten up by the wolves, and I found a big bone, and I thought, this is the femur of the elk. But I wanted to check it, and for sure there are places where there are labeled femurs of elks. I'm sure there are comparative anatomies who teach this in class, but if you go to Wikipedia, the only picture of a femur you find is a femur of a human, which is taken from Grey's Anatomy. And all the infrastructure that we have of making pictures clickable and hyperlinked and so on has not been used. This is the beginning and the end of your investigation of femurs if you go to Wikipedia. At least it was 2 years ago when I made a slide. So what's going wrong? I mean, there are people who work on Wikipedia all the time, give us lots of interesting info. Why can't we click on this particular femur and get to ostrich femurs and elk femurs and chicken femurs? And why can't we understand what is the nature of those different landmarks on the femur and what kind of tendons insert there, etc.? All the technology is there, but simply people don't convey the information because it's very boring. So you wouldn't have a comparative anatomist who spends his nights making this thing clickable. And people are willing to type because typing is quick and is efficient. But when it comes to visual information, they're not willing to convey the visual information they have. And yet people lecture on these topics all the time. If you attend a lecture in comparative anatomy, they will go through the skeleton of different animals and compare them. And so the information is there, and people are trying to teach it in some way. And if you think of how it is taught, it's taught through images. So it's all visual information. And in fact, I would make the claim that in many disciplines, visual information is the majority of the information is being conveyed. And so we are not doing a good job, not only at serving visual queries, but also in allowing experts who are the depositaries of this information to take it out of their brain and put it out in a computer-friendly way so that we can share it and deal with it, organize it, and search it. And this slide is making the same points. So where would you like to be? And so in some limited domain, this could be a vision of where we want to be. So we take the picture of the object we are curious about. By virtue of the picture having been captured and uploaded to some central repository, it all becomes clickable and hyperlinked. And so we can access the information about the seer at the touch of a finger. And this is precisely what we're doing when we ask a friend who knows about birds, what is that? You know, it's as simple as that, and we want to be able to access information. And so it feels like what we want to do is to build a bridge across this divide between information and pictures. And so we call this bridge the Visipedia, which is a play on the word Wikipedia. And so what needs to be done? And people like us who work in visual recognition, know what needs to be done. So what we need to do is to allow collections of images to be posted on the web, which is already happening. And then we need, for example, unsupervised learning to figure out all the corresponding parts between these pictures, with maybe a little bit of help from some expert. And then somebody will come in and label one of the pictures with the different parts. And by virtue of the pictures having been put in correspondence, the labels will propagate to all such pictures, especially pictures that users submit as queries. And so once the user has submitted the picture as a query, it becomes clickable. It can be linked to homologous regions in other pictures, and by virtue of that, linked to labels, which link to Wikipedia pages, and so it's all done, right? So this is exactly what we should do. And so this talk is about telling you that this is not all, and so there is more, and there are interesting questions to be resolved. And so I will not be spending much time at all on visual recognition, which is sort of the workhorse of my group, but I will talk about the complement of that. Yes?
Are you proposing then for search, or finding out information that is mainly image-driven then in this? Are you proposing both text and images?
What I want, okay. So this slide is about the fact that if we had good unsupervised learning that could figure out all the correspondences between the pictures, then the amount of work for an expert would be much reduced, because instead of labeling all the pictures that are out there, they could label only one. And you could automate the process of answering user queries because they would be automatically linked to this database of information. So at least that seems to be reasonable. And this was, so if you had asked me in year 2000, what is we should do, and I would have said, this is it, this is our mantra, this is what we want to do, and once we've done it, it's all solved. And this is the type of work we're doing in 2000, which was indeed discovering homologous regions between different images of objects belonging to a certain category, discovering the categories themselves, and so discovering these Platonic concepts that are behind the pictures and that unify entire data sets of pictures like motorcycles or airplanes, etc. And so this is from Rob Fergus's thesis. And and this work has been, so that we call this a constellation model. The constellation model is still alive somehow. Pedro Fessenswald and Deva Ramanan improved it, so they added discriminatively trained parts, which require supervision, but they work better, and so this is a whole thing that is going on. But my point today is this is not enough. And so while I thought that the final truth is in the images, and so humans should not even bother to perturb the pure information coming from the images, because the images are the only honest party in the game. And so if we have statistics and the images and we find out anything that has to be found, well, that's not true. And so I realized that humans are needed because humans have many other means of investigating the world, and images are just one facet of the way we acquire information. And so the fact that we call that part of a body a throat, well, it's not visible, the throat, right? So any side of the neck looks like any other side of the neck. But since we can cut people up, we can find out that one part of a neck is a bit different. And also, since we can, if we get hit at the playground when we are children, here it feels a bit funny and painful, while if we get hit on the side, it's less painful. And so we know that it's a special place. Okay? And so there's a simple example. So here is another example of what goes on. So this is a card made by the Louisiana Forestry Department to help people identify the ivory-billed woodpecker. And so here there are some people, so as you know, the ivory-billed woodpecker has not been seen in the wild probably since 1930, but there are every year 1 or 2 people who say, oh, I've seen one. And so the Forestry Service has put out this card to help people realize that there are lots of other birds that may look like an ivory-billed woodpecker in some configuration of flight. And so, you know, how long would it take to gather all of this information, the images and so on? You need experts in the field who have the experience, who are able to sieve through the images. I don't believe that with unsupervised learning we would be able to solve this task, unless we were paving the woods with camera, etc., and you know, for 30 years, not possible. And so the world, if you open your eyes, is full of attempts at conveying visual information. And here, you know, nobody who hasn't taken apart a locomotive engine is able to tell you that some panels are engine access and not the bathroom for the driver, etc. So it's simply impossible. So again, you know, you need in-depth, literally information in order to be able to label these pictures. But this is all valuable knowledge that we can accrue on the visual side. And so the question is, how do we get this knowledge to come in the open and to be discussed and to be in computer-friendly format? And so the picture I would like to draw is a bit augmented with respect to what we had before. So not only we have information and a bridge between information and visual queries, if you wish, but also we have to take into account the fact that we have lots of partially labeled images out there, and this is something that people in computer vision have been aware of, and so maybe we can take advantage of all of this partially and partially labeled stuff. Computer vision people build automata, and so it would be nice that the Berkeley segmentation engine was online and working on any image that I submit as a query, and the Caltech UCSD bird fine-grained classifier was there available, and etc. So we have lots of automata. Now, as I was saying before, we have experts in all domains, and right now in the field of computer vision, we always have that the computer vision person is also thinking that he's the expert in teaching the system, but it's not true. We simply don't know. There are, there is so much knowledge out there that we have not even the first inkling of, and so we would like to build a system where the experts, like in Wikipedia, they can come in and they can interact with the system without the assistance of a computer vision person, and they can convey the knowledge. At the same time, the system should be like a vampire. As soon as an expert is around, it should not only facilitate, but it should suck all the knowledge it can out so that it's available to everybody else, even to other experts, because experts have different degrees of expertise and also different schools of thought. And I'll come back to this concept a little bit later. Now, all of us have been using paid annotators online, and we know that we can crowdsource visual tasks, and I'll talk about that in a little bit. And so somebody's laughing in the back of the room because they are afflicted by this at the moment. And then, of course, we have vision scientists around. And so wouldn't it be nice if the smart student who builds a good piece of software couldn't check in this piece of software that processes images and does something useful into Visipedia, like you check in a new page of Wikipedia, and other people could edit it, and the system could figure out if it's reliable as much as it has to figure out if an annotator is reliable or an expert is reliable. Okay? And so, first of all, we have to notice that there are 4 different groups of people on this slide. Okay? And each different group of people has a different function, different properties. It's a different resource or a different user type. Right? Second, we see that the so-called ground truth is shifting. So while we're used, and I'll come back to this in the last slide, while we're used to the idea that there is some expert who has annotated a data set and provided a ground truth that we can use for training an algorithm, here there is no ultimate source of a ground truth. Well, you could say it's the experts. Well, the experts will disagree, and we know it. And they may have different views on how to address a certain visual task. And so there is no ground truth any longer. In some way, the ground truth is a platonic, hidden, latent concept that we wish to get at, if any exists. And so we would like to discover what are the different ways in which we think about images and different styles of thinking that different experts have, and see if there are agreements hidden somewhere, and if there are disagreements, bring them to the open. So it's a whole set of new tasks, and again, there is no ground truth, and we hope it to emerge. And so the question is, can we build such a system that networks machines and people and helps the community, the world, to share visual knowledge, manipulate it, organize it, etc. So I'll do now, so here you've got the overall philosophy. Now I'll go in depth into a couple of projects, 2 out of maybe 8 that are ongoing or have happened around Visipedia. And then at the end, I'll try to draw some conclusions. Okay? And so today, what I would like to do is, I told you I will be orthogonal to computer vision. I will focus on the question of how do we know whether annotators and experts are giving us the truth, and what is the quality of their work, and how do we make the system be better than any one of the experts or of the annotators, and somehow become the sum of all knowledge. And so I'll start with Peter Wellinder's thesis. A piece of it which was published in NIPS 2010. And so the question that I'm going to talk about came up as we were collecting the first bird collection called CUB 200, which included 200 species of birds mostly found in California. And this was done again in collaboration with Serge Belongi. And the way we collected a set of birds was we looked up the Latin names on Wikipedia, and we used the Latin names as indices for Flickr.com to download the pictures of the birds. And so I must say it was both, we used the Latin names, but also the English names. And so that was the source of much trouble. A fairly trivial type of trouble is if you type pelican, you get lots of pictures of actual pelicans, but then you get boats called the Pelican and restaurants called the Pelican, and you have to kill all of those images that don't belong, right? A more subtle problem is this one, the indigo bunting. And so the indigo bunting is a beautiful little bird, and it happens to be very similar to an unrelated bird called blue grosbeak. And so they're almost undistinguishable to the untrained eye. And so here you have some of the ones and some of the others. So, so these are results of typing indigo bunting into Flickr.com 3 years ago, 4 years ago. So you get some images that are clearly not correct, and some that might be ambiguous, and some that are absolutely obvious. And you would like to filter out the images that don't belong and be left with the indigo bunting images. And you do that with annotators. Now, if you do it, you obtain the commonly known phenomenon of inconsistent labels. So if you have 4 people who have labeled your images, some images have agreement and some images have disagreement. And so what do you do when your experts or your annotators disagree? And so the common wisdom is that you take majority voting, and maybe you collect some more annotators' labels if there is no clear majority. And the theme of the next 10 minutes is, no, you can do much better, but truly much better, if you think a little bit carefully about what's going on. And so I want to go through what we did. So first of all, I want to remind everybody, probably no need, but there are 2 types of errors that people make, misses and false alarms. Now, we happened to annotate, I think carefully, the indigo bunting data set, so we have a ground truth. And so we're able to see how different annotators did on the task. And so each dot here is the performance of an individual annotator. And you don't see error bars here, but some of these annotators annotated maybe 200 images, and some did only 10 images. And so the error bars are a bit different throughout the plot. And I wish I had a plot with error bars. So here, the axes are slightly different from the usual ROC because I flipped the vertical axis. And so we have the best performance is the top right of the plot. Okay? So the hit rate is on the left, and the rate of correct rejection is on the bottom. And these are equal error curves. Okay, so these are the ROC curves that you're used to, but flipped around. And as you can see, there are a few people who are around 10% error rate. But the vast majority is around maybe 25 or more. Okay, so there's a first realization. Annotators that you train with a few training pictures are not very good. It turns out that when you, and I'll show you pictures later, in most tasks I know of, when you ask experts also disagree 30% of the time or 25%. These are not outlandish. So when you find experts agree 90% of the time, then they're not even worth their salt, because then it's an easy task. Okay. So how do we think about all of these dots? And so the point of this graph is to convince you that if you simply average the opinions of different annotators, you're going to do terribly. So here, first of all, we have the good ones, the competent ones up there. Now, as you can see, there are some that we call bots, where most likely somebody was watching TV and clicking at random the yes and no buttons. Or somebody had written software to reply automatically to our queries and earn the money anyway. Now you have people who are optimistic and always say yes. Some of them might be really good. They just happen to be biased towards saying yes. And some of them may be like bots. And so you have to be careful about that. And some are pessimists. And so I was surprised that you find all of the above sprinkled somewhat evenly throughout this plot. And you find a few adversaries as well. And so I was telling my students to energize them. Oh, these must be MIT students who are trying to mess with our data. And so. But in fact, it's probably people who were confused by the GUI and clicked yes where they should have clicked no, and vice versa.
Did you just show them example images, or did you say, this beak is slightly different than this beak of this other type of bird?
So in this case, we were showing them example images of what the bird should be, and of course we cleaned up 200 birds, and so we had automated the process of generating the instructions page. We later learned that it's better to spend 20 minutes, 15 minutes to help them get qualified, but then that would require, in this case of 200, now 1,000 birds, it would require quite a bit of work in figuring out which birds could be confused with the current bird that you are watching. So it's a little bit of so that's also another very interesting question we're getting at, which is how do you train the annotators in a way that it can be automated, and so that takes advantage of the errors they make in order to generate and this is something that Jen Patterson, and in fact, Andreas Krause is also working on this question at the moment. He came through Caltech recently and gave a talk, nice talk. Okay, so once we realized that the annotators were all over the map, then we decided, let's think carefully about what annotators are doing, and maybe by thinking and having a model of what they do, maybe we understand better how to integrate that information in a productive way. And this is what we think the annotators are doing. And so let's see if I can get you to follow me. If people like bubble diagrams, they will have a great time in the next few slides. Z is the binary variable that denotes whether the object you're looking for is present or not. And so I should qualify, this is about binary tasks at the moment. And so later ask me if you want to know how you generalize it. Okay, so Z is a binary variable, and the index I denotes the image I. And so the image I is II, and it's a product of two sets of variables. One is a binary variable ZI that says one indigo bunting is there. And then you have an enormous number of nuisance variables that you don't care about, and yet they determine the megapixel image that you will capture. So which viewpoint, what was the weather, which specimen of the species it was, etc. Okay? Now, let's suppose that you had the best possible bird watcher. The bird watcher and any human looking at birds would reorient themselves, ignore all the brush or sky or waves and so on, look at the bird and identify the different parts of the birds and carry out a few, maybe 10, maybe 5 measurements on the bird. What's the color of the plumage, the shape of the beak, the overall shape of the bird, the estimated size, a few things like that, okay? So X sub I is a vector, a small vector, maybe 5 or 10 scalars, which are the measurements that your best bird watcher would carry out on the image. Now, our assumption, and so, anyway, so our assumption is, let's think of xi as a scalar for a moment. It's a vector, but a scalar for a moment. Our assumption is that the measurements that the bird watcher will make are sufficient to discriminate most of the time the bird. They are the only thing you can go by. So here we have one characteristic xi, such that condition on z being 1, the value is high, and condition on z being 0, the value is low. And so it's clear what the annotator would do. They would find a threshold and decide based on that. So if you had a picture like this, it would have a very low value of xi. It would be an unequivocal no. If you had, okay, and okay, what happens now? What happens now is a true annotator, one that you hire, will not necessarily be perfect, and so their readings of the bird will be corrupted by some amount of noise. Okay, so in the head of the real annotator, there is a variable y sub I sub j, where now j is the index of that annotator, and it's corrupted by some noise process sigma j, which we model as Gaussians. We've tried both Gaussians and long-tail distributions. Doesn't seem to be making a difference at the moment. Okay, so now we have what is in the head of a real annotator. So a real annotator, given that the ideal one would have xi in their head, well, they have a certain spread of outcomes for that specific image. And depending on how good is the annotator, the spread will be smaller or bigger. Now, if you have a clear indigo bunting, then you would have a high value of xi. And if you have an ambiguous bird that nobody would know, would be able to classify it, may be in the middle between the two distributions. And so the different annotators would have a different spread around those target values, if you wish. So I'm coming to that, yes. It's the next slide. Thank you very much. And so this is the bias idea. So you set a threshold to make it take a decision. And if the threshold is high, then you're one of those pessimistic annotators. If the threshold is low, you're one of those optimistic annotators. And if the threshold is bias. Yes, yes. And so the point is there are two separate variables. One is the bias and one is the incompetence, if you wish. And now I will convince you that there is a third variable, which we call the school of thought, and it's actually the classifier. So now let's remember that those measurements are multidimensional. And let me use the hawk and seagull example just to make the point clear. So how might you decide whether a bird is either a hawk or a seagull? And so one thing that most people notice is hawks are brown and seagulls are gray, no matter what the species would be. And the second one is the hawk has a more robust and hooked bill than the seagull, which has a more straight and smaller hook. Okay? And then, of course, there are other differences like the talons versus the web feet, etc. There are 3 or 4 other obvious differences. Okay, so here we are in a higher dimensional space, and it's clear that you could have people who train themselves or are trained to discriminate the birds just by looking at the color and didn't notice the beak, and people who might instead have noticed the beak and not paid attention to the color, and people who may be able to use both at the same time. Okay, so if you want to come up with a label, you have this high but not too high dimensional space of measurements, and you will use a classifier, which in our model is a linear classifier. And so, no particular reason other than simplifying the code that we use for estimating these models. Okay, so here is our model. And so on the left, we have the variable zi, which is what we would like to know. On the extreme right, we have the label Lij, which refers to the image and the annotator who has produced the label. The labels are observable, and there is another observable node, which is the pairs ij, of which annotator j observe which image I. And so we have labels, and we know who generated the labels. And that's the only thing we know. The labels are binary. What we would like to know is the binary value of the I, which is down there, 3 or 4 bubbles below. And so how do we do it? And so the claim that we make is that if we're able to estimate the latent variables of the images and of the annotators, we're better off at estimating the zi. And why would that be the case? Well, because annotators will see many images, and so if we're able to estimate how good or bad annotators are and what biases they might have from a subset of images, that propagates to other images, and so that helps us. The same, some images may be easy, and some very difficult, and not even the Albert Einstein of bird watchers would be able to resolve them. And so it may pay off to estimate this latent variable xi that tells us if the image is right at the edge between the two distributions of the two categories we're trying to discriminate, or whether it's fully in one or the other of the two distributions. Okay, so in some way the latent variable x helps us explain away errors that some annotators will make and still let those annotators be good annotators. So, so the idea is that you start from the labels, you want the zi's, and you do that through estimating the xi's, and then the incompetence of the annotators, which is the noise that they add.
To estimate the xi, you have to impose some law. You have to decide the number of dimensions.
Yes, and so in our experiments, the number of dimensions was not let be a free parameter. We imposed dimension 2 because we wanted to visualize well the data. And for some experiments I'll show you later on clustering, we had 4 dimensions. It turned out to be a good one. Okay, so that's an excellent point. Yeah, so ideally we would have a prior on the number of dimensions and estimate the number of dimensions as well. We don't do that. And so and the other 2 characteristics of the annotators I would like to remind you are tau j, which is the bias, and wj, which is the orientation of the classifier plane. And we call that the school of thought of the annotator in a somewhat grandiose way, but it illustrates what it is about.
Multiply tau j by wj and get unnormalized vector.
Yes, exactly. So that's what is in the guts of the algorithm. But qualitatively, they are different things. Okay, so now let me show you experiments. So first of all, the raw performance. This is what we get for the indigo bunting data set. And so we had to compare to previous ideas on how to do things. And the green line is the majority vote, and the blue line is when you use the model. And you see quite a big difference, namely with around 4 annotators, the blue model does as well as the green model with maybe 20 or 25 annotators. So it's clearly, there is a big advantage. And then there are other alternatives. So, so we carried out a few synthetic experiments to see if the idea would work and if the code was correct. By the way, the code is online. It's called Cubam, C-U-B-A-M. And Noah Snavely of Cornell told me he downloaded it, used it, and it works. So it's maybe Tsungi also has used it. I don't know what's your what's your experience. Whether Tsungi has used it and stopped using it, so maybe it doesn't work so well. Okay, so so this is a synthetic experiment in which we produced 180 of these fuzzy ellipses, each one of which had an orientation between 0 and 179 degrees, so 1 degree at a time. And we show them to annotators, asking them, is the ellipse more vertical or more horizontal? Meaning, you know, when it's 45 degrees, it's right at the threshold, but if it's more than 45 degrees, it should be labeled as vertical. And so, of course, you would expect that when we show them ellipses that are at 45 degrees, then they are difficult. And so we asked annotators to label them. And okay, and so on the x-axis here, you see the actual orientation. And confusingly, Peter decided to use 0 for the 45-degree case and minus for less than 45 and plus for more than 45. And on the y-axis, you see the latent variable xi. And in this case, it was a one-dimensional xi. And what you see is that, indeed, xi is around -1 when the orientation is, let's say, 10 degrees less than 45 degrees, and +1 when the orientation is more than 10 degrees above 45. And so you have a certain plus or minus 10 degree confusing area where the estimate of xi is quite smoothly changing between one and the other. And so from this plot, you see that the ensemble of the annotators, the average of the annotators is not biased either way. And so really at 45 degrees, if you hit 0, and some annotators have some signal, but it's not univocal in some way, it's still ambiguous, up to the point where when it becomes easy, and vice versa. Now, why does xi saturate here? And so this is because in the inference, so I didn't tell you, so how do we infer the latent variables? And so we use some variational blah, blah, blah technique that all of you have had the pleasure or displeasure of using. And so what we do is we impose a prior on the value xi, which is a mixture model where xi has a mean of -1 or +1 and a sigma of 0.3 or something like that. And then we let the algorithm adjust it. But the prior influences the extremal values. And when the information is unequivocal, sorry, so I should say it better. So you have a 1 degree of freedom that you can never discover, which is the distance between the means and simultaneously the size of the sigmas, because you could scale everything up or down by a certain amount. And so what you can measure is d prime, which is the ratio between the distance between the means and the sigmas. And so you set the two means to be at -1 and +1 just to normalize everything and to regularize your estimate. And so when there is no doubt of what the outcome should be, the means go to -1 and +1. And these are the, so while here the dots refer to, sorry, now I have to go through the animation again. So here the dots refer to individual images. So we know how easy or difficult they are. And here the dot refer to actual annotators. And now we know what their bias was because we can measure each one of them independently against the ground truth. And on the y-axis, we find, on the left plot, we find the estimated bias. And as you can see, it's a fairly faithful estimate of what the real bias was for the annotators. And the same is the incompetence or competence that you find on the right-hand side.
So what is ground truth here?
Okay, so since we produced the ellipses synthetically, we knew what was the real orientation of each ellipse. And we knew what the real answer should have been from each annotator on each query, on each image. So we could compare for each annotator the labels they gave us at each orientation with the ground truth. And so we could estimate their bias. And so we saw that indeed the individual annotators have some bias. And so a mystery to me is, it's quite clear that the majority of the annotators, so that you have a group that has no bias at all. But then if you look at biased ones, most are biased on the positive side and on the negative side. Meaning, if I remember well all the signs, that you tend to see and you tend to oversay vertical somehow. And so earlier we saw that there was no bias in the xi for the images. And so that, I don't know, that's a curiosity I've never looked into. And here you see that, so most annotators have a d prime around 3, but a few are quite poor. Okay, these plots then, okay, it's a toy example, but they tell us that at least the software is working and the idea may have some merit. This is the second experiment we thought of once the first one went through. Try and see if we could estimate the school of thought of the different annotators. And so we generated these little cartoon characters, some of which are more green and some of which are more yellow, some of which are taller and some of which are shorter. And then we added some random splotches on top of them to confuse the matter a little bit further. And so either they're green and tall or short and yellow. And we instructed two populations of annotators differently. To some we said, click on the greener ones. And to some of them we told them, click on the taller ones. And so each one of them was instructed to pay attention to one characteristic and not all. Now, we didn't tell this to the algorithm, so we mixed up all the annotators together and we fed all the labels to the algorithm. And the algorithm produced this description of the latent variable xi. So you remember each dot here is one of the images. And so the variables x1 and x2 represent something that the annotators might be using. But the algorithm, of course, doesn't know what is it because the algorithm doesn't see the images, it only sees the labels. Now, if you superimpose for some of these dots the picture of the picture that the annotators saw, you see that there is some order to these pictures. So somehow the greener ones tend to be on the right and the taller ones tend to be on the top. Now, if you put down the ground truth, that was the ground truth. So indeed, the latent variable has separated out the ones and the others. And if you look at what the W's are, W's and taus, so it's exactly as you were asking earlier, they are these. And if you color code them by what instructions the annotators received, you see that indeed the algorithm was able to estimate plausible schools of thought or criteria for annotating. Now, a more interesting experiment is this one. So what Peter did, he mixed together 5 types of images, wood ducks, mallards, Canada geese, grebes, and water pictures with no birds. Mixed them together. And he asked the annotators to click on ducks. So what we were expecting was yeses on mallards and wood ducks and no's on everything else. And I'm sure the people from Seattle would be able to make this distinction very clear, keep it in mind. Now this is a latent space that we found. And these are the color codes of each dot as to which category they belong to. Now as you can see, something strange is happening here. If the annotators were perfect, then we should have a mix-up of on one side all the ducks, and on the other side the grebes, the geese, and the water pictures. There should be no way to discriminate between them. But in fact, in the latent space, they are separated out, apart from the ducks, which are mixed together. So what's going on? And so you can superimpose the pictures. It's interesting. So we had a GUI at some point where we clicked on the individual dots, and we saw that indeed the ones at the transition are ambiguous ones, like birds against the sun and so on, where it's not very clear what they are. So the interesting thing comes when you start looking at the annotators criteria, and that will explain why the geese and the grebes pull apart where they should all be mixed together in some sense. And so here is what happens. You have a first group of annotators who are very good at discriminating ducks and everything else.
So what does the darkness of each line mean?
Okay, the darkness means the, so we had, so the model estimates not only the plane of that, let me tell it better. The darkness is the level of competence, namely 1 over sigma. Yes. Okay. Yeah, it's always a challenge to visualize everything in one spot. But thank you. Now you have a second set of lines, which is this one, that separates out the grebes and the ducks from the geese and everything else. So clearly there was a set of people who thought that the grebes are ducks. And that's not surprising because the grebes are, I mean, it's, in some way we had seeded this disaster in them because we picked something similar to ducks. And then you have a whole set of people, you see it quite spread out there, but there are not many points, so spread out doesn't mean that they disagree, it just means that the estimates happen to be that way, of people who separate out the non-bird pictures from the bird pictures, but they don't discriminate between the bird species. So what we discover here is that there are 3 schools of thought. I should be careful in what I say because the algorithm truly doesn't know that there are 3 schools of thought because there is no process for grouping these lines and seeing that it's our eye that tells us there are these 3 groups. And so there is one piece missing in the algorithm which we haven't yet put in, which is, if you think of a bubble diagram I showed you, the statistics of how the annotators are distributed, you could think of it as coming from topics model or something that groups them. And so it's yet more gimcrackery, which we have yet to have the guts of putting in and experimenting with.
I mean, saying that there are schools of thought is a reasonable inference, especially given the lines. But if you ignore the lines for a moment, when I first saw the color coding, all it told me is that grebes are harder to distinguish and geese are much more different. It was, to me, this diagram just looked like a diagram of visual similarity, right?
Yes, so it could, okay, so that's a very good point. So in my mind, the reason why the grebes ended up being separated from the ducks and from the geese in this latent space is because there were these different schools of thought, because the annotators were well spread out in the way they separated out a space, and therefore their binary labels allowed us to spread out the different species apart from each other. Namely, you have, if you think of a grebe, you have a population of annotators that says yes, and a population of annotators that says no. If you think of the ducks, everybody says yes. The geese are the ones where a minority of annotators say yes, and the water pictures, nobody says yes. And so there is means for the algorithm to pull them out this way.
If you require the annotators as part of the explanation, couldn't just be limited in Z and X, which is just basically a signal level like this?
Okay, so the annotators are required anyway. Because unless you have the labels, you cannot estimate your x's. Now, so how do you verbally explain how these things spread out? You could just say it's sufficient that the annotator. So on difficult, what you're saying is on difficult cases, the annotators will tend to disagree, and that will keep those difficult cases apart from the easy ones, which are the ones where you have all zeros or all ones, and so it will make the difficult cases hover in the middle, which was what we saw for the ellipses. And here I say, I think we need something more structured than that. I think we need the schools of thought to see this. But it's only words. I've not proven it to you. I admit it's suggestive, but not proven. So that would be an interesting question. Okay, so briefly to show you that these things are going to be used, this is a collaboration we have with a bunch of people in the medical school at Stanford who look at sleep traces. So if you have trouble sleeping, you spend a night in a sleep clinic, you get instrumented in different ways. Maybe some of the people in the room have had this experience. And the doctors the next day have 8 hours of EEG traces, such as these ones, where they identify different phases of sleep and different events within the phases of sleep. And in order to stick our feet in the water in one way or another, we focused on sleep spindles, which are events where it looks like the cortex is communicating with the deep brain in some way. And so they are higher frequency events lasting for maybe half to 2 seconds. And counting the number of these sleep spindles in phase 2 sleep is an important metric for some cases. So what does the doctor do? The doctor will not be able to take it all in because it's too long, so they hire a technician who is certified by the American Sleep Association or whatever it is to do it. And so it's somebody who has been trained for months and gets paid reasonably well to do it. And so the annotator will sit there for a few hours and go through the trace and deliver counts and a pre-diagnosis to the doctor, who will then look at these digested data and together with talking to the patient will decide what to do. And so we're curious to say, I happened to sit at dinner once with this guy, Emmanuel Mignot of the sleep clinic, and tell him, oh, we can solve this, you know, because they have to, so the annotators come once per week, and so the patient has to wait for a week before his trace gets digested. The least important patients may have to wait for a month. Sometimes the annotators are not available. It's a big pain in the neck, and so everything is delayed. And I told him, you know, with Mechanical Turk, you can do it in a night. And he said, oh, I don't believe it. And so we started the study, and this is the bottom. Yes, I'll show you how well it works automatically. That was also my reaction. It's very easy. And he says, oh, I've been working with people in the electrical engineering department at Stanford for 3 years, and they haven't been able to crack this problem. So I conveniently forgot who is it that they work with. So these are all the annotators on Mechanical Turk. So each dot gives you a sense. So we have a whole process to find some semblance of ground truth and being able to analyze this data. It's not easy at all. But anyway, so the dots here and the darkness is how many sleep instances did they annotate. And as you can see, the darker dots, which are the people who work harder, are a little bit worse than most of the lighter dots, many of the lighter dots, which means that the lighter dots that are in the top right are just flukes. They're lucky people who did annotated 3 or 4 sleep phases, got easy ones, and got away with flying colors, but they're not necessarily the good ones. So the people who work a lot have precision recall around 0.6, if you wish, and the curve is the aggregation of all of the work of all of these people. And here we have a comparison with the paid technicians. And again, the darker squares are the paid technicians who work most. And as you can see, the paid technicians are either equal or a little bit better than the consensus of the paid workers. But for diagnostic purposes, they're indistinguishable. They're quite similar. So this is, seems to be a useful thing. And the algorithms are the blue dots, different settings of the algorithm. Okay, so let me skip this one. How much time were you thinking that I should take? So up to noon or up to now? Or I have another piece of the talk, but I can skip it easily. No. 1:45, another 5 minutes, 10 minutes. Okay. So, okay. So as you may imagine, so the next thing to try out is for some images, you see that they're easy after the first 3 or 4 annotations, everybody agrees, so you should retire them. And some images are difficult, you should leave them there for a little bit of time. The same for the annotators. Annotators, as soon as you know their parameters well, you can kick them out if they're not good, or you can use more of their services and you already know how well they're doing. And so the labels they give you are much more informative. And so, as the system takes off and is being used, it becomes better and better. And so you should be able to make do with fewer labels per image. And so that's something that we've looked at. And so you can use sequential probability ratio testing to decide if an image is a positive or a negative. And so as you receive your votes, the probability that it's a positive or a negative changes for every vote, and at some point you reach enough confidence that you can retire the image. And I'm not showing you the math here, but the math is very simple, so I'm happy to do it on the board later. And what we find is the x-axis here is images that we have put into the system, and on the left side is the first few images that were labeled, and on the right side is the last few images that were labeled. And what you find, and the vertical axis is how many labels do we have to accumulate per image. And what you see is that at the beginning, there is a burst of maybe 100 or 200 images on the left, where we need to obtain 10 or 20 labels each to be able to reach a conclusion, because we're not terribly sure about whether the annotators are good or bad. And as the annotators become more and more of a known entity, the number of annotations drops. And here, we happened not to retire the bad annotators, and therefore there's still a little bit of noise, but not much. Okay, let me skip this. So we have a whole set of thoughts on how to not only do binary, but also do continuous annotations like clicks. And so here we had an experiment with which we counted all the taxis in Manhattan by downloading the big Google Earth pictures and counting them. And I think that there were 25,000 at the time when we counted them. And so this is an easy image, but as you may imagine, there are difficult cases like here on the left where there is shadow, and so the color of the cab is not so obvious, etc. Okay, I'll give you very quickly another similar but quite different thing that you can do. And so here is the story. Suppose that you had a naturalist who, with her graduate students, who goes to Costa Rica and wants to count the species of beetles in the forest. So they go out with good cameras, they spend a month, and they come back home with 30,000 images of beetles and leaves and so on. So how could you figure out how many species there are? And so if you look at the papers on beetle classification, you see strings of papers, maybe 3 or 4 papers in a row, to decide if Corsica has 3 beetles or 4 in a certain region. And so they look at every single hair on the carapace and the legs, the gonads, and this and that. So it's long discussions. So how could you quickly sort things out, maybe in a night by crowdsourcing task, and decide how many species there are? Again, if you did it by hand, it would be many years of work. And so, so the difficulty clearly is that if you crowdsource it, each annotator will not have the context. They will not see all the pictures. They will only see a few hundred pictures and will form an opinion based on very few. And also, different annotators may have different ideas on what to look for, whether it's the forelegs, the hind legs, and so on. So how could you do it? So let me go quickly through this. So for clustering, one possibility is to embed things in a Euclidean space and to use a distance, or you use an affinity. How do you do this? And so, of course, experts use different techniques. And so how would you do it? And so I must admit that this project was suggested to me when I bought this wristwatch. And I thought roughly that I knew what I wanted. And so I went to Amazon. And I found it. So in June 2011, there were 67,000 men's watches. So I realized, okay, this is horrible. I'm never going to go through. Luckily, they have a few little dialogues on the left. You can choose the diameter, the color of the bezel, and the thickness and the weight and so on. It turns out that they don't capture well my own gut feeling of what I was looking for. So For example, and so the idea would be asking people to cluster these watches by looks so that then I can, as soon as I find one I sort of like, and can look at similar ones, like people do on Pinterest, for example. Okay, so a very organic form of organization. And so here, for example, though, you could imagine that some people might say that on the left you have black watches, and on the right you have white watches, and somebody else might say, oh, no, it's sport watches versus dress watches that counts. And so, both are valid. And so how do you think of it? And so in order to work on this, we devised a GUI where we asked people to cluster things in a free-form way. And so we had lots of objects from, I think, Zappos. And so people, our annotators, could pick out, so they would see the 6x6 panel, and they could pick out arbitrary colors and use the colors to denote clusters they saw. And then they could also have the option of leaving some things unclustered if they didn't belong to any cluster. And so they would annotate, for example, shoes in red, handbags in blue, and jewelry in green, etc. So, so what is going on in the head of these people? And so what is the parallel of the model we saw? And we think that the thing to be added to what we saw before is a metric of the space, what is similar and what is different. And so if you think of these birds, maybe you think of them perching versus flying, or you think of the species of the seagull as important. And so what you could think is that different people have a different metric. Some people have a metric like this, and some people have a metric like this. And so this is what the additional ingredient for annotators that we didn't have before. So the metric they use for the space. And so our bubble model is similar to before, but it has this notion of a metric. So earlier we asked them to classify things, and now we ask them to decide what is similar and what is different somehow. And so the labels now are a little bit more complicated because the labels are labels on pairs of objects and not on individual objects. And so there are a number of changes to the bubble model that you saw before. And I'm not saying that they're obvious. It took us some time to figure them out, but somehow the philosophy is similar. And so you can think of a situation where you ask people to tell you in patterns of 6x6 what is similar to what, and then you run inference on a certain model, and you derive some clusters on the whole collection. So no single annotator has seen even 5% of a whole collection, and all the elements of a collection have been seen by some annotator in different groupings each time. And so you try to mix things up and to get lots of measurements. So I'll show you quickly some experiments. So one we did was on the popular 15 scene category data set of people using computer vision. And so this was in 4 dimensions, and we'll only show you 2. And so it looks like the clusters like 6 and 2 or 5, 7, 10, and 3 are superimposed. But in fact, if you look at assignment entropy, it's very low. So the clusters are separated in the other dimensions. And so this is what people find. These are clusters that people find, which are unsurprising. But the surprising part is, if you look at the confusion matrix with respect to the real ground truth of each annotator, all the confusion matrices look different. And so each annotator did have a different criterion for doing the clustering. And so this is the first clustering. As you can see, so the inferred cluster is a column. The real labels are rows. And so what you find is that the first cluster has 3 categories together: kitchen, living room, and office, indoors. The second one has open country and forest together. The third one has tall building and inside city. And the other ones are separated out. And so what we discovered is that if we ask people, so for each inferred cluster at this stage, if we ask people to do the task once more, but just limit it to those images of a cluster, then we get a further round of clustering. And so what you can do is you can keep reclustering until only one cluster is found. And so you have a tree structure of sort of a taxonomy of the images. And so indeed, the first cluster gets separated nicely in the second round. And so you get kitchens, offices, and living rooms, no problem at all. The second cluster mountain by itself. And okay, so this cluster here, which was the cluster, the highway cluster, which was no problem at all if you look at the ground truth, got separated out into 3 clusters by annotators. And clearly, what they see is that there are some scenes with lots of traffic, some with no traffic at all, and some with some traffic. And so these are new clusters that are made. And so this covers something that was not there in the original data set. So we have lots of experiments on birds, etc., but I will skip them in the interest of time. Okay, so so this picture you've seen. So there are a bunch of papers on other aspects that I've not been able to discuss today, and you will see it in the slides that I gave you. Maybe one last thought, and this is not in the slides I gave you because I made these slides afterwards, is the following. Our traditional point of view on what we are doing as a profession is that we are the computer science experts, and by using machine learning and computer vision techniques, we produce a black box which maps data into labels for some user. And we obtain some set of labeled data by asking an expert to label the data for us. And then we have sort of a ground truth. And the ground truth, together with our expertise in machine learning and computer vision, allows us to train this black box. And once the black box is ready, we pass it on to someone who will use it. And they will be either happy or unhappy. Okay, that's it. And so the computer vision problem is this, right? So that's what we think. So I hope that at the end of my talk, you will have a slightly different point of view, which is that, first of all, the picture is more complicated. And so let me go through all the differences. So first of all, experts are multiple, and they will disagree. And so the labeled data are not univocal. Second, we routinely augment the data labeled by experts by shipping the data off to Amazon Turkers to produce very large training sets for our machine learning algorithms. And that is even less safe as a ground truth, but we use it. So we have a bigger data set. Then we train our black box. And what happens is, and this I didn't go over, but as soon as the black box is there, the expert will start using it to explore the data, and they will realize that they disagree, and they will realize that there are lots of things they can discover that they didn't think of before. And so they will change their judgment as to what are the real ground truth labels. And I'm very happy to give you details later. And so here you have a loop that keeps going on, and they keep changing their mind in terms of what they want to label, really. Furthermore, there are multiple people in our business, and so there are lots of different possible machine learning and computer vision boxes that produce different black boxes that can be used, and they should be used. The users are willing to do some work sometime to obtain information, and this is something that Steve Branson is exploring. And it turns out that the users can help the machine a lot in achieving its goals. For example, the machine gets confused when it looks at a picture of a bird, of where is the bird, and it can ask the user, please touch with your finger the eye of the bird. And so the user, in just 200 milliseconds, will give invaluable information to the black box that will make it possible for the black box to identify the bird for the user. And so we have a loop here. And the machines themselves can be used as a third round of labeling for data that can go back to the experts, and the experts can check whether the labelings are good or not and give them to the machine learning algorithms to digest. And so my view is that this is a visual system, and so we should broaden our horizons and embrace the big mess that is here on this slide. I find it very interesting, and we should make it work for us. Thank you.
So in one of your earlier slides about FEMA, all right, you get something from FEMA, and then sort of information kind of stop right there. You make a point that even if you get the text right, you still get stuck, right? Because text itself hasn't got enough information for you there. Yeah. So I'm actually just thinking that, to me, I'm working on text processing, So text ambiguity is just as much as visual image ambiguity, the one you're talking about.
Okay,
right?
okay.
So
I accept that.
is that right? So of course, I mean, if you do this kind of limited labeling scenario, then text probably is, forgive me, very little ambiguity. That's your goal to get that
Yes.
fixed. So the question really is that for text processing, visual information can be used as grounding to help disambiguate the text ambiguity, just as the other way around.
Yes.
So-
Okay, that's a nice. And so
Right.
you say the picture is even bigger than that.
Yeah,
And
that's what I'm saying.
There's a whole world of text, and these two worlds should talk to each other.
Yeah, exactly. That's the whole point.
Okay.
Yeah. Because
Sounds-
people on text just think that the ambiguity probably is as much, even more
Yeah.
so than the image. You even can see that text you have to think about in your brain, right?
Yes.
So how is your thought about bringing them together? That's
So-
pointed out by your earlier example on the female.
Right.
example there. You have to
So I have an example of something that I don't think we published in Rob Fergus's thesis. At some point we had figured out that in order to, so we're looking for cutting corners for training classifiers for objects. And we realized that if we type words into Google Images or Bing, we get an enormous number of images, maybe 25% of which are related to the concept, okay? And so we discovered that our unsupervised learning algorithms, you could set them off on these collections of images, and since what was related to the search words was consistent and everything else was inconsistent, so think of pelican. You have the birds, and then you have restaurants, boats, whatnot, a shirt with a pelican on top. And so the things that don't enter into the category and are there just by chance are inconsistent with each other, while the category things are consistent. And so we could learn the visual category from this inconsistent set of images because the consistent part was lots of signal. Now, there was one exception we found, which was sometimes a search query produces a number of self-consistent clusters, and this is where you're going. For example, if you type Madonna, you will get a pop singer, and you will get paintings from the Renaissance of the Virgin Mary. Okay, and so there are two separate clusters of things that refer to Madonna, and so using vision, you could discover that the word has a multimodal meaning. And so now, I mean, this is a very simple example of what you're talking about, but so I'm aware of it, and it's but nobody has yet exploited it or explored it. Yes.
That's one of the things.
Yes.
Okay.
Okay. Done.